And with this, it's my very great pleasure and honor to introduce our first keynote speaker, Dimitrios. I hope I was not too bad with your last name, Vytiniotis. I repeat, to make it hopefully better. Dimitrios started his academic career with his studies at the National Technical University of Athens, and then he moved on for his PhD at the Pennsylvania University, and after that he spent some time with Microsoft Research in Cambridge, I believe with the Haskell team, and now he is with DeepMind. Dimitrios has done work in all different aspects of programming language design and implementation, and also applying the PL techniques to other areas, in particular in the last years, to making sure that machine learning algorithms scale up. And this is the topic of his keynote today, and I'm very excited to hear what Dimitrios has to tell us. So please welcome him together with me on stage with an applause. And Dimitrios, the stage is yours now.
Give me a few minutes, a couple of minutes to set up.
You have.
Yep, so I think this works. Time, I can see the time. Okay, great, so let's get started. Thanks very much for having me here. It's a great honor. It's really actually my first big conference talk after many, many years, like before COVID, really. So I'm honored and terrified. So this is the work that we've been doing in DeepMind for the past several years, and it's about scaling machine learning models, really. And we're going to start by talking a little bit about what is a machine learning program. And a machine learning program is really the numerical. We're going to refer for this talk to the numerical computations that are used for training or serving machine learning models. These are n-dimensional array programs. They consist of linear algebra ops. Typically, the types are statically known rank, dimension sizes, and these programs are generated through Python tracing. For example, from high-level frameworks like JAX or PyTorch or TensorFlow that you may have heard. And because they are traced out, you don't see algebraic data types, you do not see dynamic control flow, or very little of it, and they're typically purely functional. So, down there you can see an example of a training step, where in Python, where basically a training step takes the parameters of the neural network, the optimizer state, and some samples, a mini batch, for example, computes the gradients of the parameters with respect to the gradients of a loss function with respect to these parameters, and then applies the optimizer to update the parameters for the next step. So training a neural network is really just a big process of training steps. And these programs are generally easy, right? I told you, purely functional, no interesting data types, no control flow. However, they are computationally very, very intensive. So we have reached the point where we need more than 10 billion petaflops to actually train some of the state-of-the-art neural networks. And just to kind of put this in a bit of perspective, if you had 4,000 NVIDIA A100 GPUs, which is not the top of the line, but it's kind of a pretty beefy accelerator, you need to keep them training continuously for about 3 months. And that is assuming that they reach peak performance, the nominal peak performance, which is very difficult to do, ignoring any communication, synchronization cost, and also ignoring system failures and restarts, which are actually quite typical in a data center deployment scenario. So, so these kind of programs run in big clusters, and this is a figure from a recent Google Cloud offering for some accelerator setup. For the purposes of this talk, I think it would suffice to think of these systems as devices and topologies. So there are the accelerator devices like a cloud TPU v4 up there, which is basically a device that has some local memory. It has some units to accelerate specific operations like matrix multiplication. And then these devices are getting connected into interesting interconnects. So this is a figure again from public Google Cloud. Well, this is not for TPU v4, it's for TPU v5e, a slightly different variant. But the way the TPU chips are organized in this setup, for example, is that they're organized in TPU pods, and a pod is a collection of this kind of TPUs connected by a fast local network. It's called Inter-Chip Interconnect Network, ICI network. But you can also go across pods through the data center host network. So you have this kind of hierarchies of communication hierarchies in these offerings, and a lot of that stuff is actually known externally. So there are papers about the TPU architecture and interconnect. If people are interested. Now, of course, you need parallelism, right, to train this kind of model. So the simplest, more traditional form of parallelism is what people have been calling batch parallelism, where here you have like two devices, and they share the same parameters. So, for example, the parameters would be loaded in each of the devices. They would be shared. And then you have one batch or one shard of the batch if you want going into one of these devices, another one going to the other device. And there's some computation that computes the gradients with respect to the parameters. This is if you've heard of the term backpropagation. So this, there's some forward execution, some backwards execution of the gradients. And finally, you get to produce the gradients for the parameters. But what you need to do mathematically for this to be correct, you actually need to reduce, you need to sum the gradients from the multiple devices together and make sure that every device gets that sum. And then every device can proceed to independently update the parameters. So the parameters are kept, if you want, shared by virtue of the update function happening in all of the devices. This is a specific setup. You know, there's various variations of data parallelism. But the important thing here is to notice is that you do need this communication in between. You do need this synchronization in between. From around 2020 onwards, it was pretty clear that that certain parallelization strategies emerged. So if you want to parallelize a program, it wasn't a completely unstructured way of doing it. And some of these strategies were motivated by the need to scale for these large language models that everyone is hearing about these days. So, okay, data parallelism pre-existed, but certain forms of parameter sharding appeared, like Megatron-style parameter sharding, optimizer gradient sharding. I'm just throwing some terms here and some papers on the right. And the key thing for this conference is that these were all strategies that were, it was a small number of them, they were easy to describe at a high level, and they composed. For example, there's this kind of nice paper here down left, which was actually a study, an experimental study of what are the effects of composing these strategies for large language models on GPU clusters. And some people attempted to even do search over some kind of higher level strategies. Like that, this FlexFlow paper from in the middle. Okay, right. So just to give you a small flavor of the strategies, I've told you about batch parallelism. I'll tell you about a little variation of data parallelism, where basically on the right, you see there that the parameters are not actually shared on the two devices, they're also sharded. But in order to compute the gradients for the parameters, or in order to compute forward the network, you do need the full parameters. So what do? Right before you need the parameters, you issue an all-gather communication primitive. You get all the parameters on the device, you do your computation, but then, you know, that big tensor that you just collected from all of the devices is very short-lived. So actually it doesn't matter too much. You can just throw it away and you know, use effectively that memory space for activations as you proceed executing your network. So whereas previously the full parameters were live on the devices for a very long time, now the full parameters come on the devices for very short amounts of time. And also, you don't need to compute to keep the full parameter gradients on both devices all the time. Instead of having an all reduce on the gradients, you have a slightly cheaper operation that's called all reduce scatter, which basically reduces and scatters the gradients. So every device gets a shard of the gradients. And then the update is actually an update on the local shard of the parameters. So it's kind of an interesting variation that reduces a little bit the communication time. The all reduce becomes reduce scatter, reduces the optimizer time from the computation, but in exchange, it adds more communication and also improves the memory on the device. So it's a really complex trade-off of things that are happening at the same time. How do you figure out what is the right thing to do? And there are forms of model parallelism that I'm not going to go into a lot of detail, like pipelining, and forms of model parallelism where you shard the parameters, but then you need to synchronize the activations of the network at various points. Let's not go through a lot of detail in this slide here. So parallelization is hard, as I said. Even for these structured forms of parallelization, there is a lot of trade-offs that you have to take into account. And you're given a model, you're given a TPU system, for example, or a GPU system, and you have all these kind of strategies that you need to pick the specifics of these strategies and how to compose them. And also, the other thing is that happens if you are a machine learning engineer, but that also happens if you are a systems designer. So you're a systems designer, and you are given the new architecture for the new GPUs or TPUs or accelerators, and you have some representative models that you think they're going to be used in the future, and you want to figure out, okay, how much memory should I actually have on every device? What should be my interconnect type? Should I be using a hierarchical system, a switched system, a mesh? What is my ICI domain size? How many devices should I have on the fast network, and how many devices should I let them communicate through a slower host network, for example? What should be my host connectivity? How much bandwidth should I put? How many NICs should I put per host? And the key thing to note here is that you should not really penalize a system design just because you picked a completely unsuitable parallelization strategy for that system. So it's kind of parallelization and system design kind of go hand in hand. And that was kind of our first intuition. Before I jump a little bit to what we did, I just want to tell you that there is a very, very nice software abstraction for these kind of systems, which is viewing them as n-dimensional arrays. So here on the left, you have a 2x4 hierarchy of 2 servers, and every server has like 4 devices. They're connected in a ring in this case. I don't know why. And you can view them as a 2-dimensional array where devices D0, D1, D2, D3 are kind of local to one server, and D4 to D7 are local to the other server. And these kind of n-dimensional system views are convenient, and we like them when we talk about parallelization, because it's very easy. It's easier to reason about communication. So you know that if you want D0 to D3 to talk to each other, you can go through the local network per server. But if you want D0 to talk to D4, D1 talk to D5, D2 talk to D6, and D3 talk to D7, you have to go through the host network, and that could be more expensive, and the links could be oversubscribed. So I just want to say that it's a convenient abstraction that we're going to be using in the rest of the talk. Okay, so composing strategies with meshes. So meshes and composing strategies is a really good match. So here we see 6 stages of pipelining. Pipeline is composed of 6 stages, and within each stage you do 64-way data parallelism and 16-way parameter sharding. So you can think of a cluster of 6 by 64 by 16 devices. And the very first thing that we did here is that we decided to, since we want to talk about composition of the strategies, we decided to come up with a little modeling DSL where actually programmers, systems designers could actually sketch some of these strategies. So we had a little IR that composed of computable blocks that described abstractly the input shapes, the output shapes, the parameters, the flops, and the memory requirements for a block of code, if you want, communication primitives, and some constructs to nest parallelization strategies. So here's how it would look. You would say in this example here, you would say this is a pipelining consisting of 6 stages, and we're going to name the mesh axis we're going to be using. And then within each stage, you're going to do 64-way data parallelism, and then within that group of devices, you're going to do 16 ways model parallelism. And the actual computation you will be doing is a sequence of transformer layers, for example. And a transformer layer is self-attention, which is one of these computable blocks, followed by some communication on the model axis, more computation, and then more communication. So some human had to take one of these models and actually script these strategies. But the benefit was that we did have a very concise description of these strategies. Now, if you take this kind of little DSL and you in addition, you write, on the other hand, you expose a target system interface, basically an interface that tells you how many flops you have per device, how much memory you have per device, what's the memory bandwidth you have per device, number of devices, and also a way to map some kind of, to map the software, the parallelism axis into the physical topology axis and an analytically computed cost, then you could actually simulate these programs, these strategies very easily by just writing an interpreter. So you could say, I'm going to the simulate function has a signature, takes a computation and a target system and gives me back some metrics. So that's kind of what we did. And we had some internal validations, but we also did the brave thing of taking an external paper that had one of these big studies on a cluster that we did not have access to. And we tried to see, given what is publicly known about this cluster and what is publicly known about this paper, can we simulate it? Can we get the same results? And we sort of did. If you see that figure up there, the thick lines is what our simulator predicted, and the dashed ones is what the actual experiments found for several configurations. So the trends are the same. The absolute numbers differ a little bit because, well, again, we didn't have access to really tweak our roofline models or network models. But what was even more exciting is that once you have this little DSL, you can track everything. You can track cost centers, and you can actually enumerate programs in this little DSL by code which is as simple as writing this kind of silly comprehensions that you see down to the right. And that gave you the ability to do systems co-design. So, for example, here we have an 18 billion transformer model, a medium, small for these days transformer model on a cluster of 256 GPUs. I'm not going to tell you much about the topology, but what we did there is we wanted to investigate if every device has 80 gigabytes of memory versus if we start shrinking the memory that's available per device to all the way to 6 gigabytes, what's going to happen to our throughput? And the important thing to notice here is like the two arrows, is that if you go from 80 to 15, there is an impact. There's a moderate impact or small impact to throughput. The interesting thing to notice here is that this first column has a different parallelism, optimal parallelism strategy than this column here. So you change a little bit your parallelization strategy, and then you mitigate the effects of cutting the cost from a system. And then the other interesting thing here to notice is that if you really push the limits to the extreme, you say every device has 10 gigabytes or 6 gigabytes of memory, it's actually still possible to parallelize, but you have to introduce more interesting parallelization like pipelining. And you see this because of these green things that measure the pipeline bubble, which is some inefficiency introduced by pipelining. So despite the inefficiency, it was actually better than just picking a different parallelization strategy. Right. And I just want to kind of mention in tangent this kind of work that we did here, which it stemmed out of the previous work, which was, I talked to you about this kind of software parallelism and about viewing the hardware as an n-dimensional array of devices. And it was the obligation of the target system implementer to really express that mapping. But what we wanted to explore here in this paper, we wanted to say, well, actually, you could systematically explore the possible mappings. So that's kind of what we did. So why not? We have basically a tensor of required software parallelism and the actual n-dimensional array of devices. And there is a systematic way to enumerate the mappings, possible mappings. And then once we had that, we wanted to say, okay, now that we have this mapping, can we actually decompose collectives like all reduce to smaller primitives, smaller collectives like reductions, broadcast, reduce scatter, and all gather to make the reductions run faster. And that's what we did in this paper with Ning Ning. So it's a pretty interesting, nice extension of this work. Okay, well, okay, after that work, was it time to pack and go on vacation? And not really. There was still a lot of problems in this kind of work. And the problems are the following. First of all, it was a modeling DSL. It was not a solution for actually partitioning programs. Second thing is that as new papers emerged and new techniques evolved, we often had to extend the DSL with little extensions that we didn't really think about in the beginning. And it was getting a bit too messy and too low level, and we didn't like that very much. Then the other thing is that a human has to write the abstractions of these models, which is error prone. They may forget some collectives. And then Finally, really, when you execute a neural network, the image is not so simple. So, for example, you have a backwards pass. The reductions, where the reductions are actually going to happen, they don't happen all at the end. Once you finish with the backwards pass, reductions could happen, depending on how the backend compiler schedules things, could happen in the middle of the computation. And we just didn't have good ways of describing this kind of scheduling improvements and possible overlapping of communication with computation. So we really wanted to kind of go after the IR that was actually going to execute, not a modeling IR. But we wanted to still maintain the same high level of abstraction when people describe the schedules, these strategies. So this is the birth of the part-IR project that has been our main focus for the last couple of years. It had like 3 goals. One goal was we wanted to enable teams that didn't have ML system experts to easily and automatically scale their models. So this is a large number of researcher teams with, let's say, medium or small compute footprint. They need a few TPUs, a few GPUs, a few devices. But then we also wanted to enable the teams that specialize in large models, the ones that have the machine learning, the systems expertise in them, to easily express, debug, and combine custom strategies. These teams, they knew exactly what they were building, what they wanted to build, so they wanted to kind of instruct the compiler stack to just do the right thing. And this was a small number of specialist teams, but with a huge compute footprint. So the product in both cases was quite big. And finally, we wanted to still enable the use cases that we had before, like co-design, or also use cheaper and less contented hardware, older generation hardware in our data centers. So I'm just going to have one slide that tells you all the good stuff you get or that you would want to get, and then I'm going to tell you a little bit about how we got to some of these things. So the machine learning researcher writes their training step. They just write the math of the model, no model modifications, nothing to do with systems there. They just pretend they have a giant supercomputer that can run the model. Then they organize their devices in a mesh. And that requires a little bit of expertise sometimes. So I would say maybe that's the least kind of nice part of it. So we haven't automated that part, although we had all this previous work that could possibly do it. Then they write a schedule. So a schedule is a little bit like the high-level descriptions that I described before, but in a more traditional schedule, if you want, for this kind of community, Halide schedule style, where you actually, one by one, you tell the compiler what to really do. So in this case, the schedule says, partition my samples on the 0 dimension and axis batch. And then it says, once you're done with that, find automatically the best model parallelism using the model axis. And once you're done with that, shard the optimizer state along 0 dimension. And also, we ask the users to provide some hints to help, especially with the automation part. If you have, for example, repeated layers, you don't want the search agent to really repeat exactly the same decisions for all layers you have. You just want to kind of, you really want to repeat the same decisions for every layer. You don't want it to search and rediscover. And then what you get back is you get back a partitioned device local function and some metadata. And the metadata says, how was the function actually partitioned? What do you need to do? How do you need to invoke that function? How do you need to shard the inputs and outputs of the function to actually invoke it? And also some per tactic metrics. For example, after every tactic, what happened with the communication primitives? What is the estimated runtime? What's the memory? What are the flops? What else? Yeah, I think these things. Now, that's really nice, right? The machine learning researchers can just take the math and run it with these little scripts. Literally, the actual code is that long in most of the deployments we see. So let's see how we actually did that. I'm going to start from the beginning. How do we actually get these kind of array programs from JAX that I told you about? So here on the left, you have a function, and the function multiplies the input x with 2 weights. So W is a tuple here in Python. And so you take W0 and W1, you just multiply x back to back with it. And JAX offers this kind of JIT transformation, which is effectively, it says, take the Python code, trace it out. While you trace it out, construct an array program in a lower level IR. This is the stable HLO MLIR dialect, which is an array IR that effectively wraps the XLA array language, which is what the XLA Google compiler ingests to compile for GPUs or TPUs or CPUs, and then runs these things. So that's what happens. And I mean, you will notice here that W in Python, that would be a tuple really, but in MLIR, it has been teased out into 2 arguments. So this is what I said before, this is the impedance mismatch between the Python program and the actual low-level program. The low-level program doesn't even have tuples in most cases. It has just arrays. Now, JAX also offers some transformations. So JAX.grad is the automatic differentiation transformation that's offered. So here, if you take the grad of the same function with respect to its first input, the parameters, what you expect to see some code. You don't need to read the code, but what you need to read is that it returns 2 values, and they correspond to the 2 gradients for the 2 W's, the W0 and W1 that I mentioned before. So that's how we get from JAX to these kind of array programs. And a full training step, well, it's really a jittered step that includes the gradients and the optimizer state, and you get like these kind of really verbose programs that include matrix multiplications, but also a lot of random number generation for some layers, or also vector ops for optimizers and whatnot. So, right, how does our system work? So the system works at a high level. We take this part.ir JIT. So we start from this kind of JIT entry point as well. We have a variant of it, part.ir JIT, and that accepts also these schedules. We trace out, like JAX, to stable HLO, and then we go into our compiler stack. And our compiler stack rewrites the programs according to the schedules, or also according to some of these tactics involve automation. So for that, we have a search algorithm that is using a simulated cost model. This is the simulator at the level of the IR that I described before. And the simulator, again, like before, takes a target system specification and a low-level IR and gives you back some metrics about it. And then finally, the program comes out and gets compiled by the XLA backend compiler, but now that code also involves communication primitives as well. So, okay, so here's the key idea of part.ir, one of the key ideas of part.ir. The theory behind it is based on linear algebra homomorphisms. What do I mean by that is, if you have a dot operator, like a matrix multiplication, it takes 2 tensors, 16 by 32 and 32 by 64, you get out a tensor of a matrix of size 16 by 64. You can actually view it as producing the output along the 0 dimension in chunks, where every chunk could be produced by a smaller matrix multiplication of a slice of the first operand with the full y second operand. And this tile 0 says that you should stack all the chunks together on the 0 dimension again. So, of course, there's more ways that you can see a matrix multiplication homomorphism. You can say there's the contracting dimension as well, the dimension of size 32 here in the middle. So you can say, if I slice my first operand on dimension 1, and if I slice my second operand on dimension 0, then if I do a matrix multiplication, every time I get a chunk of 16 by 64, the full matrix size. So what do I need to actually get the right result? I need to sum all of these pieces together, and this is expressed with this reduce business here. So you have these tiling loops where effectively the monoid about what you should do with the local computation, should you stack it or should you reduce it, appears here as a little attribute in the IR. And some notes is that the loops themselves bind to specific mesh axes. And that is actually convenient for the parallelism story that I'm going to describe later on. So you can think of, you can think that this restricts the way you can nest the loops. So you can never nest these loops in ways that are not allowed by the mesh you have available. So you can never double nest the same axis in a loop nest. That is gonna let you lower these programs in a SPMD fashion in these meshes very easily. But the second thing to notice is that the semantics of this is not really tied to these axes, so you could view these axes as just annotations, and you could ignore them, and you could lower these loops sequentially as loops that actually concatenate in the end or reduce in the end. And in fact, that's what we do for our reference interpreter. So that was kind of idea number one. Idea number two is that, okay, we have a generic way of expressing these homomorphisms, which we call the tile mapping registry. And basically, it says here, if you want to produce the output in chunks in dimension 0, you should be slicing the first input on dimension 0 and leave the second one untouched, the second operand untouched. There's another one for the output dimension, but also it says if you want to produce the whole output, you could actually do a reduction where you slice the first operand on dimension 1 and the second operand on dimension 0. So it's really like a coding. Think of it as a sort of a refinement type for this kind of linear algebra operators. It's a succinct coding of these homomorphisms. And there are other ways you could express this with affine maps, for example. I just want to stand on the engineering benefits of having a registry. So first of all, it allows you to bring your own array dialect. So if you want to partition a new array dialect, other than the XLA dialects that we've been thinking with, it's very easy. You just bring a new module that describes the registration of this dialect with these homomorphisms. The rewriting code is actually shared across many ops, and it's very easy to kind of concentrate the behavior of the system in one place in this tile mapping registry, and also to incrementally add more mappings. As you discover, for example, that some operator is very tricky, you don't really understand its full homomorphism behavior, it's very easy to just add another one at the point when you discover a new behavior. For example, for scatter op, XLA scatter op is a really complicated operator, and initially, maybe we supported, I think, just batch parallelism. But then over the time, we discovered some more interesting behaviors, and we started adding more and more and more mapping. So that was easy to do. And it is a fact that we have not seen semantic bugs over 2 or 3 years of development. I think mainly because of this separation. So we never had like rewrite code, pair op rewrite code. We just had this kind of centralized rewrite code we just ran once. So the trusted code base was small. So once we had that, we could actually define compiler action spaces. So the compiler APIs now can expose some of these tiling actions. So this is a tile action here. If you see a value, which is a tensor, you can say every value can be tiled, can be expressed as a loop that on every iteration just slices a piece of that value and gives it back to you. So we called it initially, because it's very dumb, we called it dumb tiling. It's how you bootstrap, it's how you start creating the loops in your program. And then the second API, compiler API that we exposed was propagation. So if you have a dot operator, here a metric multiplication, and you see that the first operand is actually produced by a loop, you could actually convert the dot itself to become a loop guided by the tile mapping registry. And then later on, if you're going to compile for temporal, you could fuse the loops. If you're going to compile for SPMD, you didn't really need to, but you could do it. But the thing is, you create more loops out of existing loops based on this kind of homomorphisms that you have. And we had propagation going from operands to ops, as I described here, propagation going from op uses to ops, and also sideways propagation going from one operand to other operands. Right, now, we have the action space, that's very nice, because now it can be targeted by either manual partition tactics or automatic partition tactics. So, for example, an ML systems expert would say manual partition my inputs on dimension 0, and samples was a full Python tree with like 3 array values in the leaves. What you could get, actually, you could get these 3 actions that said tile argument 55, 56, and 57 on dimension 0 along the axis badge, and then propagate the consequences. And the agent could also be picking arbitrary things and say, oh, tile argument 4, or tile argument 16, or tile argument 24. So our agent was exploring a tree of actions, really. And the right loops will be inserted by propagation thanks to all of these linear algebra homomorphisms. Right, I just have one slide about automation. Automation was really important because it accelerated research and model iteration, and it minimizes really the manual labor, especially for teams that do not have experts. And it has been used, and it's been used particularly for models where people have unknown or not universally agreed upon sharding strategies, like graph nets are an example of this. We used Monte Carlo tree search because we exposed these imperative actions, so exploring one action at a time and trees of actions seemed like a very good fit for it. And why does it work well? The reason it works well is because we thought very hard about how would a human partition a model. So humans would actually try to shard some of their parameters, and they would expect that the matrix multiplications inside the models would be sharded along the data. So we exposed a little work list to the agent that only included the function arguments, and the agent was actually able to pick from these. And as we tiled some arguments through propagation, other arguments became obsolete. So the search space started shrinking very drastically as soon as you started taking some right decisions. And also, humans know that they have repeated layers, so we don't need to independently search for them. So we asked users to tell us, if you're using repeated layers, tell us some grouping, that we should not repeat the same choices. And yeah. So how do we lower these loops? As I said, these loops could be lowered temporarily. In fact, they are lowered temporarily in the reference implementation, but they're lowered mainly to SPMD parallelism, single program multiple data parallelism. So we introduced a separate dialect for that, separate language for that, IR, slightly lower level, where you take one of these nested loops, loop over axis X and loop over axis Y, and you flatten the nested parallelism out into flat parallelism over both axes, and inside the region of code tells you what to do on a per device. And that IR also included types to express distribution, replication, and explicit collectives and distributions. And it came with a proof of correctness, which will be released when we release the paper at some point. Here, the paper on the right is a paper that is actually open. Does not describe the lowering, but gives you a good introduction to part IR distributed types, and also how to optimally compile a redistribution operation to lower level collectives. Okay, so how do these types look like? If you have an axis, if you have a mesh X and Y, and you have some data that's replicated on all of these axes, basically, you can think that types have a global denotation, which is what is the value, what is the value that they actually capture, but they also can get the local type per device. So part IR redistribute commands never change the global denotation, but they change the actual physical distribution of the data. So you have a distributed tensor here where all the data is replicated on all devices. You can issue an old slice on the y-axis. So then the top devices get only the top data and the low devices get only the low data. And then you can all slice on the x-axis, and then all devices get the left data and the right devices get the right data. And then you can also all gather all of them back and you get back to the original type. So you can go through collectives and implement this kind of redistributions. And as we part IR SPMD had a global view of the computation, had this kind of distributed types, but we wanted to compile to device local code. So for that, we introduced an intermediate level of abstraction, which we called part IR MHLO, which effectively was like part IR SPMD, but had the local view of these collectives. Instead of having these complicated types, I talked about the global denotation, it had this kind of local types here. And there were optimizations that were easier to express if you knew the global denotation, and there are optimizations that were more convenient to just express if you just had the local types here. And this is a higher level variant of the XLA collectives that actually talk about device groups. So we introduced kind of this higher level of abstraction at that point. And I just want to kind of stand to this point for a little bit. One lesson we learned is it's very useful when you try to build the right level of abstractions for the transformations you want to make, because that helps you reason, be correct, test them. So for example, here's a transformation from a paper that appeared in OOPSLA23, which says if you see a matrix multiplication followed by a reduction and a scatter, then you can actually rewrite it to hide the communication cost of this scatter in a loop. Without going into a lot of details, that loop allows you to overlap a permutation with the actual dot general. So it's a little bit like it has a systolic array flavor to it. And the key idea here is that we introduced some abstractions that were not in the array language we were working with, XLA or MHLO, that made this code very easy to debug, view, reason about. So, MHLO, XLA does not have a structured for that tells you the static number of iteration count. Okay, it doesn't have a collective rotate. So this is rotating the data, sending the data to your neighbor along a specific axis. So all the devices of a specific group send to their data to their neighbor. And also we introduce this kind of collective with a slice and a shift. That also doesn't exist. So expressing this very succinctly was very nice because we would implement this in a little pass, whereas the actual implementation, at least the original one in this paper, was baked in with code generation effectively in the partitioner. I want to talk a little bit about MLIR. So MLIR is a framework for defining dialects, and it has been very useful for us because it allows us to share languages and constructs and operations from other languages. So we didn't write any array operators, and we didn't write any compiler infrastructure ourselves to manipulate and write passes for these array operators. They all existed in the MHLO dialect, which someone else had developed. When we import to PartIR, we pattern match on some of them and we introduce some of our custom ops. So we have a soup of, let's say, MHLO array operators and our own operators. And that's happening at the PartIR level as well. We introduce these loops on top of the existing IR. And then when we lower, we remove the loops of PartIR and we introduce temporal loops, for example, here. And then when we lower even more, we remove these loops and we introduce PartIR MHLO collectives or for loops. And then finally, we export to MHLO. So MLIR is a great framework for adding constructs, removing constructs, expressing the invariance at every level of your stack. So as I said, it's a framework to define dialects and passes. It standardizes the compiler data structures across different projects. And that really means that diverse engineers from different teams actually speak the same language now. And it has a lot of things that we value and love from building compilers in functional languages, which is my background. So for example, it makes it relatively easy to define rewrite rules and patterns in declarative ways. And also, the compiler implementation itself pervasively uses value semantics for things. So it feels natural, easy to learn, and combined with good C++ practices, it's actually a pleasant experience. And it is easy to reuse other dialect attributes, types of operation or operations, which means that it really fosters collaboration. So there are teams working on various compilers across Google and the rest of the world, and MLIR really gives them a kind of a common point to talk about and develop things and share things from each other, and also adds a sense of shared infrastructure ownership. Everyone owns this infrastructure; it's for everyone. And really, we in our team we do have some compiler PhDs, but we do get mostly very good engineers, and they're not compiler experts. They come from a Java background or whatever, and they very quickly turn into proficient compiler engineers. And I think largely because of this framework and guidance from our team. Okay, so a good idea that we had in this project was to actually separate the partitioner from the backend compiler. Some people keep asking, why is a partitioner part of the compiler? Is it not a part of the compiler? What is it? In this project, it has been very beneficial to separate the partitioner from the compiler because it enabled innovation around the partitioner. So if you think about a core compiler team, like for example the XLA team or then whatever team each company may have, they have to tend to everyone's needs, and everyone's needs are not the same. The compiler team has to actually prioritize things and design things right for everyone. Whereas if you actually think about it, there are different teams with different needs, and going from a monolithic compiler to an adaptable compiler stack, it's really important. So just to give you some examples, by ingesting stable HLO on top, we were able to introduce some custom operators for specific needs. So for example, to express better vectorizing transformations from the source level, or to express some extensions for MPMD computations that I'm going to talk about in a bit. And then also after we exit the compiler stack, other teams, because this was not inside the compiler, other teams were able to take the program that we emitted and actually do more interesting rewrites to it. Like, for example, rewrite the communication collectives in ways they found would be better or optimal for the specific runtime that they were planning to run these things on. So the only wish I had in that point is that if only the backend compilers expressed some more APIs and hooks for the upstream compiler components to drive them and help them steer to not undo things that the upstream compilers wanted to happen. So I want to kind of mention one good thing, which is incrementality. Incrementality, I talked to you about these kind of actions. You do tiling and propagation that keeps rewriting the module. So that's actually very, very good for this kind of conflict resolution problem that we call. So here, the colors are not very visible, right? So here you can say you want to shard the 0 dimension of the batch, but you also want to shard dimension 1 of the parameters. Because this is the diagram that I showed you before. You shard the batch and you shard the parameters. So the problem is that this dot, this matrix multiplication, potentially could be sharded on the 0 output dimension or on the dimension 1. Which one should we have picked? And the answer is that if you do these choices sequentially, you are in better luck than actually throwing these constraints to the compiler and let the compiler figure it out. So here you say tile batch on dimension 0, and you will get a loop. And then you say tile the parameter now on dimension 1, and you will try to get a loop, but you cannot double nest, right? So you cannot further partition the dot. It's already partitioned on the model batch. So what happens? Well, you just have the dump tiling of the parameters. And if you lower this program, you will get the old gather that you expect on the parameters. So doing things incrementally really helps with this conflict resolution business. There's the other approach, which is you add all your sharding constraints at once, and you let the compiler figure out what to do. Or if the compiler doesn't do what you do, you ask the user somehow, or maybe the user finds out what to do. And here I have some plots that actually show that, yes, it is really important to, if you try to do blind, just throw all the constraints and let the compiler do its thing, even this kind of compiler, it's not going to perform as well as if you had resolved the conflicts, either with internal constraints yourself or with this kind of sequentialization that I described. Right, and I really only have 2 more slides. Okay, so that's what we've done. I think you have a good overview of the whole system. So what comes next? First thing that comes next, things that we are thinking about or we will be thinking about in the future, beyond SPMD. SPMD is good, but it's very uniform to have these meshes. In reality, you want to have like heterogeneous systems, clusters of GPUs and TPUs or different sized clusters. So you want to move really from SPMD to data flows of SPMD or MPMD. On the automatic partitioning side, I told you that sequentialization is good for conflict resolution, but there are still cases, especially in some exotic models, where you do need some internal guidance, even in part IR, because taking one choice for the input may still require to do some interesting thing in the middle of a model. So we have some work to automatically discover exactly the right places where you need to make a choice. And the challenge there is you don't want to expose too many intermediate points because you're going to really make your search space blow up. You want to just figure out the right intermediate points. Then we would like to revisit the rewrite-based propagation. So the algebra homomorphisms, great idea. Using loops themselves, maybe. It is good in terms of semantics, but actually we rewrite the module. And rewriting these kind of huge modules of like 500,000 ops continuously while we do search is expensive, and it's expected to be expensive. So could we somehow combine the good ideas of this kind of algebra homomorphisms and some ideas from layout propagation or sharding propagation from GSPMD to make things faster? And the other thing is, when we go to extreme scale, you don't expect that you have a program to run, I don't know, 4,000 TPUs I mentioned before, or more actually, to run without failures. Things are going to fail. So how do you recover from these failures? And do you perhaps push the problem to the runtime and you say, hey, please runtime, give me a view of the system that, where there is no There's no failures of virtual system, or do you virtualize everything, or do you actually try to make the IR itself more aware and the API more aware of the failures, and you provide recovery mechanisms? And I have a hunch that this could be related to kind of declaring effects and effect handlers in the program to tell you what to do in this case. And the challenge here is, again, how to do this without changing the model code. Like we never want to change the math of the program. Okay, right. And I just want to conclude. How will the future AI compilers look like? So this is some predictions, or maybe just kind of my wish list. I kind of like these ideas, but I don't know if they will ever become true. So I think we should be going to compiler components, not monolithic compilers anymore. We should be defining, there's the backend compiler and the partitioner is kind of one example. Custom teams have custom needs, and the compiler pipelines should be adaptable, basically. But that also means that you need to make sure that some of the actions, some of the requirements for some of these compiler components should kind of be exposed by the downstream compiler components. I expect that we will see progressively more use of search and AI, especially for problems that are not like time critical. You don't need to compile within like a very small budget. So I expect to see more and more hierarchical and learned cost models and techniques like Monte Carlo tree search. And I think really the other thing that intrigues me in this space is that compilers compile, especially in big organizations, compile hundreds or thousands of programs every day. And that's a lot of data and a lot of optimizations that are happening. And that data is not collected very well to really kind of inform us about what is the actual compiler choices that have been done here, and how could we use all the data across users, across compilations to really learn something and improve our compilers. So if you think about a compiler passive or a compiler component as a service, that could be a service for everyone. Every user of XLA could be using it. What can we do in that space? Right, and with that, I'd like to thank you. This is a bunch of the team and collaborators, and I will take questions in the rest of the time. Thank you.
How do we handle questions? Please walk around. So questions, please. Someone will bring you a microphone when you...
Hello, thanks. Very interesting talk. A lot of these optimizations and tweaks that you let the programmer do, just from my own experience, they can be quite unpredictable. So the programmer themselves they have to go through a cycle of trial and error until they actually optimize the code. So it looks like really long-term, the only solution is to allow these, AI programs to write themselves, right?
Yes, so we try to make the debugging experience easier because we have these imperative schedules. At least they can get early feedback. So, they say, I want to do batch parallelism, and they get metrics back, and the metrics say, you've inserted, all gathers. Oh, dear, I didn't expect an all gather in a batch parallel program. Something has gone wrong here. They require a little bit of expertise, but it's actually better than writing all the constraints, let the compiler do something, go run the program, trace it, figure out it's slow, figure out which collective is slow, and then going back. So we try to make this through simulation to make that process less painful. But yeah, automation. Some users don't want to bother with this, and they just go for automation. But I would say yes, there are search aficionados who really, really love the search and just put it in their models, and it's kind of just stuck with that forever. No one has turned back from search. Someone was telling me yesterday. But, not everyone trusts search yet. Yeah?
So, thank you. And I'm probably going to use the wrong terminology for what I'm saying, but I think that my question will be clear despite me using the wrong terminology. Okay. So perhaps you said it, but I was wondering, this language that you are proposing that allows to talk about how to architect the system, does it have a component where it observes the throughput or other runtime properties and then changes the architecture at runtime?
No, I mean, you're talking about the first part of the talk, like that little DSL, right?
Yeah, yeah.
No,
Why
it was
not?
just purely
I would
simulation.
have thought that this is a good thing to,
I mean,
to try.
It's done mostly in simulation. So in simulation, you would get a cost, but we never tried kind of taking the schedule and mutating it or rewriting it based on what we observed from simulation to get to. So we didn't try to kind of explore, mainly because it was so simple that we could typically we just enumerate the whole space and we just get points for the whole space. But I see your point, with more and more complex strategies, which that DSL didn't really capture. It captured like it's a small set. You would need to explore a little bit.
Hi.
Hi.
Hey, Dimitrios. Thank you for a very nice talk. I just want to piggyback on your answer to the previous question that people don't, many people don't usually trust into the search. So in order to build this trust, do you envision that any of the research we do in verification and formal methods would be useful? And if the answer to this question is yes, then what kind of verification would be the most viable in this setting?
Oh, it's not a matter of trusting in terms of correctness. They say, I think it's a matter of, it feels it's like too opaque for them. I mean, correctness, as I said, we really never had a correctness bug. Correctness, occasionally we get bug reports for correctness, and that has to do with verification because the numerics change subtly because we introduce all reduce, right? And all reduce moves a reduction, which was inside the metric multiplication unit, outside to go through the network implemented somewhere else. I don't really know. So we do get occasional issues like that. The training is not as stable as it used to be. Maybe verification could help with that, but then I don't know how to mitigate it anyways. Like, you do want to parallelize. It's very difficult to mitigate. And the other relation where verification could be interesting here is that we have this tile mapping registry, and it's about homomorphisms, but people in the team have sat down and said, oh yeah, this is a parallel dimension. Let me add 1 and 0 and null here. Oh, this is a contracting dimension. We add 1 and 1. Some, no one has actually verified that stuff. We've tested the most tricky ops with exhaustive testing. Exhaustive testing. But it's unverified. So, yeah, I don't know.
Maybe I have a question myself. So, thank you very much first for the talk and amazing amount of work, and I hope the ML algorithm people appreciate what you do to make ML pipelines scale. Now, you mentioned the MLIR as a very good platform that has enabled a lot for your team. And I fully understand the pragmatics. My question is, do you see any need for research there? So as far as I am informed, this is basically an SSR-based intermediate representation. Do you see need for other intermediate representations that might be better suited for ML?
It's a good question. Like occasionally, so MLIR is for everyone. Is a semantics-less framework sort of. It's really a data structure, but it's really engineered to allow you to talk about SSA dialects or this kind of blocks with arguments, which is the modern way of doing control flow. But I think there are some interesting language design questions, IR design questions there, which is say you want to support forms of dependent types. The current MLIR framework doesn't really allow you to do that very nicely. So, how do you extend there? So, language design, IR design questions exist. Changing dramatically the IR to something different, I don't know. It has been useful so far to us until now, but I didn't know that before. So before I also thought that we would need abstract syntax trees and Haskell-like, functional programming-like data types. But it, as I say, seemed fine. We all know they're isomorphic, right, to some extent. So I don't know. There's interesting language design questions, interesting type system questions. How do you encode things? Often, if you try to do research in that area, you will be bogged down by the practicalities, which means that the memory of an attribute is owned by the MLIR context. So therefore, if you want to add a value, if you want to store a value there, that value, someone else owns that memory. So you have to really think hard about the engineering problems. Yeah.
Do you have any data on if you have an expert do the manual partitioning and then you just replace it with an automatic partitioning?
Yeah.
How much worse is this?
So obviously it varies a ton, right?
Wildly.
A ton. So for the simplest, so we actually we do have some open papers that describe some of these experiments. So we are able to discover expert strategies for known models like transformers, for example, and then for models where people just didn't know, just didn't get good manual shardings, we got better. That ICLR paper that I described, the Graphness paper, the highlight paper, was produced by just using the automatic partitioning. They didn't actually write manual partitioning at all. So there is evidence that we can find better partitions. But it depends a little bit on the model as well. There are crazy models where we are not going to do so well, especially models that require internal partitioning. So if you start to do, if you think about, just going to give you a very simple example. In a transformer, there's one specific operation called the attention matrix, computing the attention matrix, which is an attention matrix who has a size which is sequence length, how many tokens you had in your initial context, times sequence length. So it's a rectangular matrix, right? So that sequence length dimension comes from one input, comes from the original input. So it's almost like you've taken some kind of outer product at some point, right? More or less. So, okay, the input comes sharded on that dimension. How should you shard the transformer, that internal matrix? Should you shard it on the rows or on the columns? It's the same dimension. You have to insert an all gather in one of the arguments, but which one? That's an internal choice, and you actually have no option to expose it through, sequentialize it through arguments. You only had one argument, the input. So there are models that are like that need internal choices, and they're not even exposed in our search space. We're not going to capture this specific sharding. But the work that we're doing now, follow-up work we're doing now, is going to uncover these interesting points as well.
Do we have more questions? Yeah.
Thanks for the wonderful talk. I think Ilya asked the correctness, but I want to ask the exact opposite. Have you considered, I know machine learning itself is imperfect, so why not bother introduce some approximation into the optimization process? So have you considered approximate computing, maybe even analog computing, so that we can get huge speed up by sacrificing some accuracy or perfection?
So you mentioned approximate computing.
Right.
So approximating so instead of sharding, approximating the models, or are you talking about, yes, can you clarify a little bit more?
Yeah, instead of guaranteeing the absolute correctness, why not?
Oh, I see.
Yeah, why not intentionally introduce some imperfection?
Yeah, no, it's a very interesting work. It's a very interesting idea. We haven't done that so far, but it could be relevant, especially for the very large scale experiments. I have nothing to add to this yet, but it is one of the things that we would like to learn more about. Happy to connect offline if you have pointers.
Okay, well, thanks.
Maybe one last question. If you had this continual learning in your very last slide, very last item, what do you exactly mean?
Yeah,
more support for continual learning, or using continual learning to make the compilers?
Yeah, make the compilers better. So you always compile programs. As you compile programs, you kind of learn from what you did. Maybe you compile several variants, and you use that as a feedback continuously to improve your instruction scheduling, for example, or your sharding.
Okay, thank you very much.
Thank you.
And I guess we are now up for